Let's take a look at what you need to do for your lab for the three graphs. First thing you need to do is write an equation for the line. Okay, you can use the information from the box. Here's the basic line equation format. A, B, and C are all values given. And if you take a look at that equation, it is essentially a quadratic equation. Slope of the line. Well, the slope of a position-time graph, you should be able to tell me what that is. Because the line is curved rather than straight, the further meaning is, what does that tell you about the velocity? We're not going to deal with the y-intercept. We're not going to talk about and do anything with 5%. So, just a few things for this graph. Give me the line equation. Tell me what are the two pieces of information that the line and the slope represent. The next graph is your velocity time graph. So for your velocity time graph, need the line equation as you would for any graph. Tell me what the slope means. Tell me what the y-intercept should be. If you look at your graph, you should come up with the idea that y-intercept should be pretty darn close to 0. It should be, in perfect world, 0. Since that's the case, what does that mean that you need to do? You're right, it means you need to do a 5% check. Your last graph is a position times squared graph. Well, why did you make this graph? If we take a look at it, we started out with a position time graph that was curved. One of the things we learned in our first unit was when we have a curved line, we learn a couple of different ways to linearize it. And the way we would linearize a parabolic graph is to square the horizontal variables. So we linearized the position time graph. And that's why we made this one. So for this particular graph, again, I want you to give me the line equation. Second thing I want you to do is tell me what the slope means. If we write out the generic line equation, we're going to start out with displacement, and that equals our slope times t squared, because a horizontal axis variable is t squared, plus some sort of initial displacement, di, let's call it. We should take a look at this equation and see if it matches or looks similar to any of our kinematic equations. And if you look hard enough, what you'll find is it looks fairly similar to equation number 3, which looks like this. Right, in our blue equation up here, which is the generic equation of this line, the slope is corresponding to this 1/2 a term of our kinematic equation. So if we want to identify what the slope means, well, we can take a look at that. It's not the acceleration, but it's related to the acceleration. Third thing to do on this graph is to identify what the y-intercept should be. Again, if we look at this graph, it looks like it's going pretty darn close to 0. So if the y-intercept should be 0, what does that mean that you get to do? Again, you're right. It means that you have to do a 5% check this graph. In discussing your graphs, what you need to do, first of all, after you've done all the things we just talked about for the graphs, is compare the a value of your position time graph to the slope of the position time squared graph. We just identified what this is. This is 1/2 of the acceleration. And what I mean by the a term of your position time graph is it's a quadratic, so it's ax squared plus bx plus c equals 0. Again, if we look at our kinematic equations, what we're going to see is that one of the kinematic equations looks like it could be a quadratic. And if we take that kinematic equation, we can rewrite it so that it looks like this. 1/2 at squared plus vit minus d equals 0. So we've taken the displacement, subtracted it from its side, so it's on the same side as all the other terms, and now we have a 0 equation. So what we see, again, is the a term here is in the same position as our 1/2 a. Our b term is in the same position as the vi, and our c term is in the same position as minus displacement. So in number 1, where it asks us to compare the a term, or the a value of our position time graph, it should be very close to, if not the same value, as the slope of your position times squared graph. They both represent 1/2 of the acceleration. The slope of your velocity time graph, you told me earlier, was acceleration. That value should be, in fact, double the slope or the a value for your other two graphs. And so that's something I want you to discuss and compare in your lab write-ups. The assumption is that we've been doing discussion of error sources long enough. that you should be very good at figuring out what might have caused you error in your lab, and that you can cover that on your own. So you need to have this lab completed, please, by Wednesday class time, because we'll be doing another lab on Wednesday, and this one needs to be finished.